Hi there, this is Professor Shannon Gracie from Miracosta College. We are covering the final section for our intermediate algebra class. Woohoo! Um, Out of Robert Blitzer's Introductory and Intermediate Algebra for College Students. So, congratulations for hanging in there. Today we'll be covering how to solve exponential and logarithmic equations. So let's go ahead and start with our warm-up. Pause the movie, warm it up, and we'll check how you did in a minute. Good luck. All right, let's see how you did. If you guys notice, we're going to be kind of using a similar idea to this. We have the same denominator in each of these. So since we have the same denominator, don't the numerators have to be equal? So I'm just going to say that this means that, so I'll say this, since the denominators are the same, we can equate the numerators. So we'll go ahead and do that. That means that x minus 1 has to be 2, so x has to be 3. So we get our solution of x equal to 3. How'd you do? Awesome. Okay, so here we go. Solving exponential equations by expressing each side as a power of the same base. So if you have something like this, a base raised to the m is equivalent to the same base raised to something else, then using kind of a similar idea as to the warm-up, if you have the same base, then you equate the powers, right? So you would equate m equal to n. So then you rewrite the equation. Sometimes, you have to mess around with it a little to get it in that format. So you would rewrite your equation in the form of b to the m equals b to the n. If it's not already in there, you would set m equal to n and then solve for the variable. So let's take a look at this first example. So this is what you look at when you're thinking about these kinds of items. You look at the bases. Can you get the bases to be raised to the same power? So notice that 100 is a power of 10. So we keep the left side the same, and then 100 is the same as 10 squared. So 100 is equivalent to 10 squared. Now what we do is we look at the powers, all right? So the powers, we now equate those guys. So x squared, if we have 10 on both sides as the base, then the powers have to be equal. So I equated the powers. So then x squared would be equal to 3, and square rooting both sides, we have x would be equal to plus or minus root 3, and you'll see that if you substitute that in, that both solutions work out. So you have negative root 3, positive root 3, or plus or minus root 3. Okay, so go ahead and pause the movie and see if you can get part B, all right? Good luck. Let's see how you did. So I'm looking at 4 and 8, and I'm seeing that both 4 and 8 are powers of 2. So 4 is the same as 2 squared. That's all raised to the x plus 1. 8 is the same as 2 cubed. And that's raised to the 3x. So 2 squared was the 4, and 2 cubed here is the 8, so we're getting closer. So now when you raise a power to a power, remember that you multiply. So this will be 2 raised to the 2 times x plus 1 on the left side is equal to 2 raised to the 3 times 3x on the right side. So then we'll get 2 raised to the 2x plus 2 is equal to 2 raised to the 9x. So now we have the base of 2 on either side, so we can now equate the exponents. So 2x plus 2 must be equal to 9x. So then we would get negative 7x is equal to negative 2. X is equal to 2/7. Okay. So how did you do? Do okay? And you'll find out if you check it in the original, you get this is indeed the correct answer. All right, so next up. Unfortunately, it's not always that's not the format that we get all the time. So if we're going to use logarithms to solve exponential equations, this is what we do. We isolate the exponential expression, and then we take the common logarithm on both sides if we have base 10 in our exponential. Otherwise, you take the natural logarithm on both sides if you have a base other than 10. That's the convention. Then we simplify using one of these properties. So you're either going to get, and these all stem from the product rule. So you're either going to get, if you have natural log of b, some base b to the x, notice if you use the product rule, you get x times natural log at b. Or you might end up with natural log at e to the x, right? And then this guy, you'd have x times natural log at e, but natural log at e is just 1. So you just get x. Or you can think of it as you're evaluating the natural log function at the natural exponential, so you just get what's in the power. Or if you have a base of 10, you would have been taking the common log of 10 to the x, and then for similar reasons than that middle one, you're evaluating log base 10 at 10 to the x, so you just get whatever's in the power. Okay, so here we go. Let's solve these guys. Again, there's no easy fix, right? You don't have like 2 to the something equals 4 to the something where you can mess around with the bases and get them to be the same. So I'm going to add 6 to both sides, and we'll have e to the 2x is equal to 38. So now we have a natural exponential function, so we definitely need to evaluate the natural log of both sides. And then what we'll have is we'll end up with whatever was in the power, because you're evaluating the natural log at the natural exponential, and you're going to get that is equal to natural log at 38. And we're just going to get exact results here. So if we divide both sides by 2, we get the natural log at 38 over 2. And that is our result. Now be careful, you can't break into that log, so you can't cross out the 2 and the 38, all right, because that would not be okay. It'd not be equivalent. All right, so let's look at this next guy. We need to isolate our exponential, so we need to multiply both sides by 2. We'll get 3 raised to the x minus 1 is equal to 10. Now, look at the base, it's a 3, so it's something other than 10. So we're going to evaluate again the natural log of both sides. When we do that, we're going to get x minus 1 is in the power, so we're going to get x minus 1 times natural log at 3 is equal to natural log at 10. So x minus 1 is equal to natural log at 10 divided by natural log at 3. I divided both sides by natural log at 3 in that last step, or multiplied by 1 over natural log at 3, and they divided out. And then when we add 1, we'll get x is equal to natural log at 10 over natural log at 3 plus 1, but we want to get a common denominator here. So the common denominator is natural log at 3. So we'll have x is equal to natural log at 10 plus natural log at 3 all over natural log at 3. But we can do one more thing there to make it prettier. Whoops. One more time. What we can do is we have a sum of two natural logs. So x will end up being natural log at 30, 10 times 3. I'll write that out. Natural log at 10 times 3 over natural log at 3, condensing the log in the numerator. So we'll get x is natural log at 30 over natural log at 3. So that is our end result. That is the exact answer. Again, you got to be careful with your properties of logs. There's no property for the quotient of two logs. There is a property for the log of a quotient. All right? But this is the final result. Okay, here we go. 10 to the x is equal to 120. So on this one, we want to evaluate the common log of both sides because we have a base of 10 on the left side there. So this is just going to be x because you're evaluating log base 10 at 10 to the x. So you get what's in the power. So x is equal to log of 120, and you're done. The end result is log at 120. How's it going? You hanging in there? Awesome. All right. Next up, we have using exponential form to solve logarithmic equations. So here we go. If you can express the equation in the form log base b at m equals c. All right. So you have a log on one side and a constant on the other. So you're going to use the definition of a logarithm. So log base b at m equal to c means that b raised to the c is equal to m. So this works when you know what c is and there's unknown values inside the logarithm. So you solve for the variable using all the skills you've learned this semester, and then you check the proposed solutions in the original equation. You got to make sure that you include in the solution set only values for which m is greater than 0. Got to have a positive value in the log. So here we go. Here's where we're going to use our condensing skills. Notice that we have a constant on the right, and we have a difference of logs on the left that have the same base. So we're going to write this as log base 3 of x divided by x minus 2 is equal to 4. Now we know the base, we know the exponent, so this means that 3 to the 4th is equal to x over x minus 2. Now we know what 3 to the 4th is. 3 to the 4th is 81, and that's going to equal to x over x minus 2. So then, multiplying both sides by x minus 2, we will get, this side will divide out, we will get 81x minus 162 is equal to x. Subtracting x from both sides, we get 80x. Adding 162 to both sides, we get 162. So then x will be 162 over 80, which reduces to be, let's see, that'll be 81/40ths. And that's a positive number, and when you check it in the original, you'll find that it works out. Okay, so the next guy, we have common logs, the sum of common logs on the left and a constant on the right. So this is going to condense to be log at x times x plus 21. So that's all in that log, and that's equal to 2. So now remember, there's a base of 10 in the common log. So this means that 10 squared equals x times x plus 21. 10 squared is 100, equals x squared plus 21x's. So then 0 equals x squared plus 21x minus 100, because we have an equation that is quadratic in form. You can use whatever format you want. I recognize that this factors, so I'm going to factor this as x minus 4 times x plus 25. So x minus 4 is 0, or x plus 25 is 0. So x is 4, or x is negative 25. Now if you look in the original, you have a log x, so we can't have a negative in there. So this answer here is extraneous. So therefore our only result will be the one that where x is equal to 4. Okay, and then we have another type of situation using the one-to-one property of logs to solve logarithmic equations. So here we go. This is where you don't have an extra constant. You don't have something that is not part of a log. And so you express the equation in the form log base b of m is equal to log base b of n. So this form involves a single logarithm whose coefficient is 1. So you've got to use the power rule backwards, to get to where you have no coefficients to the logs. So then we use the one-to-one property. So basically, what does that mean? That means that if log base b at m is equal to log base b at n, you've got this the log of the same base on either side of the equation and nothing else. So that means, so if you have this case, then m equals to n. So you use all your mad equation solving skills to solve for the variable, and then again check proposed solutions in the original equation. You need to have only values for which both m and n are greater than 0. So here we go, our last two examples. So notice we have 2 logs on one side and 0 on the other. So that means we can add a log base 6 of 64 to both sides. So then we'll get a result of 2 log base 6 at x equals log base 6 at 64. Using the power rule backwards on the left side, we get log base 6 at x squared equals log base 6 at 64. So the m is x squared and the n is 64. So notice that you have the same log on either side. Both logarithms have a coefficient of 1. So therefore, that means we can set the insides equal to each other and solve. So then if we solve these guys, we end up getting x is equal to plus or minus 8. Now if you look at the original equation, you have to throw out that negative 8. So that one's extraneous. So your end result will be 8. Okay, and then part B, now notice that they're all common logs. They're all log base 10. So what we have going on is we've got a sum of logs on the right side that we can condense. So we're going to have log at 5x plus 1 is equal to log at 2x plus 3 times 2. So this gives us log at 5x plus 1 is equal to log at 4x plus 6 when I multiply through by the 2. Now they're both common logs, so that means we can equate what's inside. So we get 5x plus 1 equals 4x plus 6. Subtracting 4x from both sides, we get 1x. Subtracting 1 from both sides, we get 5. And so you'll find when you check this in the original equation, you get a solution of 5. It works out. Okay? So anyway, it was a pleasure serving as your instructor this semester. I hope you have a fabulous day and a fabulous math life. All right. Bye.